Hello, my name is Travis Hamilton. I'm a PhD student here in electrical engineering at Northwestern. And today I want to tell you how I can take tiny structures and see distant worlds. So how do we see distant worlds? Well, as Sam was talking about earlier, what we typically use are telescopes here on Earth and up in space. And those telescopes all have cameras on them. These cameras record pictures for astronomers to then take and analyze. Now, what if there's a planet, an exoplanet for instance, that's so far away that we can't see it and can't detect it with our camera? Now that's a problem, and I, as an engineer, I want to address that issue. And the way I'm going to address that issue is I'm going to trap and control light. And the reason I'm going to trap and control light is because I want to take that little amount of light that I'm given from that exoplanet, and I want to hold it near my camera long enough so that it can absorb and detect that light. Now, how am I going to trap and absorb this light? Well, being a good engineer, I'm first going to ask a scientist. In fact, I could ask Dr. Tyson here, and I could ask him two questions. I could say, Dr. Tyson, tell me what light is and tell me how to trap it. And his answer would be, Travis, light is made up of tiny particles. Just like how matter is made up of tiny particles like atoms, light is made up of tiny particles called photons. And I say, well, Dr. Tyson, that's interesting, but how does that help me trap light? And he would tell me, Travis, light is kind of like having a lot of kids to look after. Let's say you're at a summer camp and you have all these energetic kids. Turns out photons are also extremely energetic. And just like kids, they have a hard time staying in one place. So if you're a camp counselor, you could have these kids run around a little bit. In fact, you could set up some sort of race just to keep them entertained. You can't keep them in the same place, but you can at least keep them entertained for a little bit. And you kind of have two options. You could either have them run across a meadow, and they'd be from one end to the other in no time, or you could have them run through a forest. Now, it might not be the safest thing to do, but what this forest allows you to do is it allows the kids, or it forces the kids, excuse me, to slow down, because they have to avoid hitting the trees, and they start clumping together, and so they have to avoid hitting each other. So I tell Dr. Tyson, well, that's interesting. I guess I could make some sort of forest for my photons to slow them down and trap them, at least keep them in some region for a little bit longer. But what should these trees be made out of? Well, it turns out that metal is actually a really great material. Metal tends to reflect and keep light out of it. And so I think, okay, well, I'll use metal trees. But before Dr. Tyson leaves, what he tells me is that these trees, to be effective, have to be able to fit into the width of a human hair. In fact, not just one tree, but 1,000 trees. So we're talking about extremely small objects here. And so I thank Dr. Tyson, and now as the engineer, I need to actually make these tiny structures. And I'm actually going to become more of a baker than an engineer. Because when we were talking about this forest, the only thing that really mattered were the tree trunks. And so instead of making trees, I'm actually going to make cupcakes. They have the same round cylindrical shape, and if I make them out of metal, they should serve the same purpose. And so just like a baker, what I first need is a cupcake pan if I'm going to make my cupcakes. Now a baker, he can go out and he can buy a cupcake pan, but I, as an engineer, I need cupcakes that are 1,000 times smaller than the width of a human hair. So I can't go out and buy this cupcake pan. I have to build it myself. And the way I'm going to build it, actually, is a way you might be familiar with if you've ever taken a magnifying glass out on a hot summer's day. And if you take this magnifying glass out and you shine it onto a piece of paper, you'll actually burn a hole that's smaller than the magnifying glass itself. And the reason is, as I'm sure a lot of you know, is because you're focusing the light into a smaller beam. So I'm going to do the exact same thing, except instead of a magnifying glass, I'm going to use these tiny bead lenses. These bead lenses are 100 times smaller than the width of a human hair. So we're not quite at 1,000, but we're almost there. And instead of the sun, I'm going to use a high-powered lamp. This is something I can actually buy from a company. And what I'm going to make my cupcake sheet on is silicon wafers. I could use a different material, but in this case, I'm going to use silicon. Now, what I'm going to do, once I've actually made my cupcake pan, if I was a baker, I would go ahead and fill these cupcake pans with some sort of batter. But in this case, I have a cupcake pan with tiny holes that are 1,000 times smaller than the width of a human hair. So instead of filling them with batter and making lovely cupcakes, I'm going to fill them with metal. And what I get are these lovely metallic cupcakes that are 1,000 times smaller than the width of a human hair. Now, this is only the first step. What scientists and engineers have been theorizing over the past decade is how tiny structures interact with light, these tiny nanostructures, as you see here. So scientists are wondering, what if we make the cupcakes into triangles? What if we make the cupcakes smaller or bigger? What if we use different materials to make the cupcakes? Well, now I, as the engineer, have a tool to actually make these tiny structures and to hopefully improve our cameras and see even further into the universe than we ever have before. Thank you.